US Physics Olympiad, year 2022. F equal MA, first round. Exam B. This year Olympiad was split by two exams, A and B, and all students could participate in any of these exams. As usual, it was given 75 minutes for 25 problems. Please subscribe for this channel if you want to get more interesting problems. Problem number 1. A ball is held a height h above a slope, which is at an angle 45 degrees from the horizontal. The ball is dropped from rest. Assume the ball bounces off the slope perfectly elastically. What is the distance between its first and second impact points? Solution for problem number 1. First, let's draw the picture. From this picture we can see that height is h, and for this height the first time to travel will be t0 equal square root from 2h over g. It means that for the second impact it takes 2 times t0, which is 2 square roots from 2h over g. Now let's count what is the speed of this ball right before the first collision. That will be vertical speed equal square root from 2gh. After bounce it turns in horizontal direction, and we can count what is horizontal distance for the motion between two impacts. That will be x equal vt or 4h. And last step is to find the distance. Distance will be square root from 2x or 4 square root from 2h. That's answer D, and that was solution for problem number 1. Problem number 2. A massless wheel of radius r has 4 small masses m placed evenly along its rim. Let the moment of inertia for rotations about the center of wheel and the plane of the wheel be I0. Now consider rotations about the two axes shown, with the corresponding moments of inertia I1 and I2. Which of the following is true? Solution for problem number 2. By definition of moment of inertia, we have I0 equal 4 times mr square, I1 equal 2 times mr square, I2 equal 4 times mr over square root from 2 square, which is 2 times mr square. It means that we have I1 equal I2 equal I0 over 2. That's answer A, and that was solution for problem number 2. Problem number 3. 4 evenly spaced points are marked on a massless seesaw as shown. 2 blocks of masses 5 kg and 7 kg are placed on the seesaw so that it balances when the fulcrum is at point 4. The diagram is not drawn to scale. Now suppose the fulcrum is moved to point 2. How much mass should be placed at point 1 so that the seesaw again balances? Solution for problem number 3. If the seesaw was initially balanced, its center of mass must have been directly over the fulcrum. Therefore, the total weight force of 120 newtons can be regarded as acting at point 4. After the fulcrum is moved, balancing torques about 0.2 implies that the new mass should have a weight of double of this 120, which is 240, because distance from point 2 to point 4 twice greater than distance between point 2 and point 1. So it means that total mass must be placed twice greater, which is 24 kilograms. That's answer C, and that was solution for problem number 3. Problem number 4. A firework explodes, sending shells in all directions in a vertical plane as shown. Suppose the shells are all launched with the same speed and ignore air resistance but not gravity. A long time later, but before any of the shells hit the ground, what shape do the shells make? Solution for problem number 4. In the absence of gravity, the shells would always form a circle. Adding gravity simply shifts all of these locations downward by gt squared over 2. So the shape is still always a circle, which is answer A, and that was solution for problem number 4. Problem number 5. A swimmer swims at the speed v relative to still water. A river flows from a pier to a lake with the speed u. If the swimmer swims downstream from the pier to the lake, then back upstream, what was the average speed during the trip? Solution for problem number 5. To find what is the average speed, we have to divide full distance over full time. Suppose that full distance is d. In that case, total time to swim downstream will be t plus equal d over v plus u. The total time to swim upstream will be t minus equal d over v minus u. It means that average speed will be total distance over total time, which is 2d over t plus plus t minus. After calculations, d is cancelled, and finally we have v squared minus u squared over v, which is answer E, and that was solution for problem number 5. Problem number 6. A block of mass m is at rest on a frictionless table. It is pushed horizontally by a constant force F and has a total momentum P when it reaches the end of the table. If a block of mass 2m is pushed across the table in the same way, also starting from rest, what is its momentum when it reaches the end of the table? Solution for problem number 6. Since the forces and the distances are the same, the total work done is the same. It means that total kinetic energy is the same, and the kinetic energy is related to momentum by formula K equal P squared over 2m. It means that for constant kinetic energy we have momentum must be proportional to square root from mass. It means that new momentum for mass 2m equal square root from 2p, which is answer D, and that was solution for problem number 6. Problem number 7. Two blocks of unequal masses big M and small m are hung from the ends of a massless frictionless pulley as shown. The blocks are held in place and the entire pulley is mounted on a sensitive scale. After the blocks are released from rest, but before either has fallen off the pulley, what is the scale reading? Solution for problem number 7. When the blocks on a pulley are released, both blocks accelerate, with the heavier block accelerating downward. It means the center of mass is uniformly accelerating downward, which means the force acting on the pulley is less than weight big M plus small m multiplied by G. That's answer A, and this is a solution for problem number 7. Problem number 8. A ball is launched with a speed v at an angle theta to a fixed ramp, which itself makes a 45 degrees angle with the horizontal. Assume that when the ball hits the ramp, it bounces elastically and frictionlessly. For what value of theta will the ball bounce off the ramp 2 times and then return to its original launch point? Solution for problem number 8. First, let's use another coordinate system, which looks like this. Axis x going to incline and y going perpendicular. In that case, we have new initial velocities and new accelerations due to gravity. We have Vx equal v cosine theta, Vy equal v sine theta, Ax equal negative g over square root from 2, and Ay equal negative g over square root from 2. First, for both directions, we can count total time to travel. If ball is hitting 2 times to this incline before it returns to the initial point, it means that it traveled 3 times to up and down. It means that total time to travel equal 3 times change of vertical velocity, which is negative 2 Vy over Ay, which is 6 v sine theta over g over square root from 2. From other hand, when this ball returns to original point in coordinate x, it means that total change of speed equal negative 2 vx, and the total time to travel equal negative 2 vx over ax, which is 2v cosine theta over g over root 2. Now we have to equalize this 2 times, from which we can find that tangent theta equal 1/3. It means that theta approximately equal 18.4 degrees, which is answer E, and that was solution for problem number 8. Problem number 9. Bill is leaning on a box of mass 30 kilograms, exerting a force 35 degrees below the horizontal. If the coefficient of static friction of the box on the ground is mu s equal 0.4, what is the minimum force needed for the box to slide? Solution for problem number 9. Suppose Bill exerts force F, then the maximum friction force equal mu static multiplied by normal force. But normal force equal force F multiplied by sine theta plus mg. So it means that applied horizontal force Fx equal F multiplied by cosine theta, and it must exceed force of friction. It means that we have this inequality from which we can find a minimum force F. That will be this expression, which is 203 newtons. That's answer C, and that was a solution for problem number 9. Задача номер 10. Problem number 10. Two springs with a spring constant 2 Newton per centimeter and 4 Newton per centimeter are connected in parallel. They are both connected in series to a spring of a constant 3 newtons per centimeter as shown. What force must be exerted at the end to extend the system by 1 centimeter from its relaxed length? Solution for problem number 10. Let's mark all spring constants by these meanings. Now we can use a regular formula for calculations of parallel and series connection for springs. For spring 1 and spring 2 in parallel, we have formula K4 equal K1 plus K2, which is 6 newtons per centimeter. And for series connection of spring K3 and K4, we have equivalent constant for whole construction is 2 newtons per centimeter. It means that we have to exert force F equal K delta X, which is 2 newtons. That's answer B, and that was solution for problem number 10. Problem number 11. Water with a total mass big M is poured into a cup of a cross-sectional area A. A block of mass small m, whose density is half that of water, is tied to a thin string. The string is attached to the bottom of the cup, and the block floats in the water as shown. The atmospheric pressure is P atmosphere. What is the total pressure force that water exerts on the bottom of the cup? Solution for problem number 11. Consider force balance on the system of the block and water. The atmospheric pressure applies a downward force P atmosphere multiplied by cross-sectional area A, and the gravity applies a downward force big M plus small m multiplied by G. Now the buoyant force on the block is 2 mg, because water is twice as dense, which means the string applies a downward tension force mg to keep the block in place. To balance all these forces, the base of the cup must exert upward force P atmosphere multiplied by A plus big M plus 2 small m multiplied by G. That's answer E, and that was solution for problem number 11. Problem number 12. Two identical bricks of mass m small are attached to two frictionless pulleys by a massless string on a fixed slope of angle theta to the horizontal, as shown. Suppose that the coefficient of static friction between the lower block and the slope is μ, and all other surfaces are frictionless. What is the minimum value of μ so that the blocks can stay static? Solution for problem number 12. Let the tension in the string that wraps around both pulleys be T. Applying force balance to the upper block, we must have T equal mg sine theta. The pulley applies a force 2T to the lower block, so applying force balance gives us 2T equal mg sine theta plus force of friction. When the friction is just barely sufficient, we have F friction equal μ multiplied by normal force, which is 2 μ mg cosine theta. Now, combining all of them, we have mg sine theta equal 2 mu mg cosine theta, it means that mu equal 1/2 tangent theta, which is answer A, and that was solution for problem number 12. Problem number 13. A ballistic pendulum is designed as shown below. A uniform ball of mass m and radius r is attached to a massless rigid rod, so that its center is distance L from the ceiling. The ball has a small tunnel hollowed out. A small block of mass m and the speed v goes into the tunnel and collides at the center of the ball perfectly inelastically. Subsequently, to what maximum height does the block rise? Solution for problem number 13. First, let's use angular momentum conservation, because during this collision the angular momentum is not changing, and we can write equation that initial angular momentum for this small mass m equal mvl, and it's going to angular momentum for whole system rotating around ceiling point, which is I omega. I, it's a moment of inertia of whole system, this pendulum plus this mass, and omega is angular speed. Now let's write equation for angular momentum of this system. The equation for this angular momentum, the expression for this ball around the center of mass, which is 2/5 mr square plus ml square due to parallel access theorem, and plus ml square, that's from this small mass m, and finally that will be 2ml square, and we can write this equation. So it means that omega equal mvl over I. Let's write expression for kinetic energy, because after collision this kinetic energy go into potential energy for whole system. That will be 1/2 I omega square, and after insertion of this omega we will have this expression, and this must be equal to 2 mgh, which is potential energy for whole system. Now let's use expression for I, put it here, and find that h equal this expression. Let's answer D, and that was a solution for problem number 13. Problem number 14. A cylinder of water is suspended in a space station. Under the influence of surface tension, the cylinder splits into droplets. After a short time, viscosity causes the droplets to settle into static shapes, neglecting the effect of evaporation. Compared to the original cylinder, the final set of droplets will have next one. Solution for problem number 14. Because water is almost incompressible, the volume stays almost exactly the same. During the process, energy is dissipated due to viscosity, and the energy due to surface tension is proportional to the total surface area. Thus, the surface area must decrease. That was answer E, and that was a solution for problem number 14. Problem number 15. 5 astronauts are orbiting Earth in a low circular orbit. They decided to go around the planet following the same orbit but much faster. To set a new record for obtaining Earth, 4 of them thought they that they could quickly increase the velocity, then use a jet engine to maintain an orbit of the same shape. In the first four choices below, the red arrow denotes the direction that fuel will flow out of the jet nozzle. The fifth astronaut was skeptical about such a possibility. Who is right? Solution for problem number 15. The centripetal acceleration required to follow a circular orbit is, if the speed is increased, the inward acceleration must be increased. So the engine should be pointed outward to provide an inward force. So that's answer B, and that was solution for problem number 15. Problem number 16. A uniform rectangular block is in static equilibrium on an inclined plane and experiences gravity, static friction, and normal force from the plane. Though gravity acts on the entire volume of the block for the purposes of torque balance, it is equivalent to a single resulting force acting at the block's center of mass. Similarly, while the normal force acts on the entire bottom surface of the block, its torque is equivalent to a resulting force acting at a single point. Which of the following best shows this point? Solution for problem number 16. Consider the point of contact between the block and plane directly below the center of mass. Gravity effectively acts at the center of mass and thus exerts no torque about this point. The friction force points along the plane and thus also exerts no torque about this point. Therefore, since the block is in static equilibrium, the net normal force must effectively be applied at this point, yielding choice B. So that was a solution for problem number 16. Problem number 17. A box of mass big M is sliding to the right with velocity v on the frictionless table. A small pack of mass m/2 slides frictionlessly inside the box. Initially, the pack is at the left wall of the block with a rightward velocity of 2v with respect to the table. After a time t, the pack collides elastically with the right wall of the box. How much longer will it take until the pack hits the left wall of the box again? Solution for problem number 17. As can be shown by working in the center of mass frame during an elastic collision, the relative velocity of the two objects only changes in sign. Therefore, the relative speed remains the same, so the time until the next collision is also t, which is answer B, and that was solution for problem number 17. The following information applies to problems 18 and 19. Problem number 18. A uniform rod of length L and mass m is placed with its ends resting on two identical springs of spring constant K as shown. The rod is initially in equilibrium. If the rod is uniformly displaced downward and released from rest, what is the frequency f of its oscillation? Solution for problem number 18. If the rod is displaced down by distance delta L, then the vertical net force experiences is 2k delta L. This is just like a spring mass system where the spring constant is effectively 2k. So the angular frequency is square root from 2k over m, and thus the frequency is this one. That's answer D, and that was a solution for problem number 18. Problem number 19. Next, the rod is brought back to equilibrium. It is slightly rotated about its center of mass, then released from rest. What is the frequency f of its oscillation? Solution for problem number 19. If the rod is rotated by a small angle theta, the net torque of the rod is this one. The rotational form of Newton's second law is torque equal moment of inertia multiplied by angular acceleration. So it means that for such rod we have this equation, or this standard equation for angular oscillation. From this formula we can find that angular frequency equal this one and the frequency equal this one. That's answer E, and that was solution for problem number 19. Problem number 20. A uniform hollow sphere is initially at rest on a horizontal plane. The plane begins to accelerate horizontally to the right with the acceleration a. If friction is high enough to prevent the sphere from slipping, what is its translational acceleration? Solution for problem number 20. It's easiest to begin by working in the non-inertial frame of reference or plane. In this frame there is a fictitious force on the sphere directed to the left. This is why it's negative ma, effectively acting at its center. Taking torques about the contact point with the ground, we can find that moment of inertia, which is 2/5 mr squared multiplied by angular acceleration, equal torque, which is force of friction F multiplied by radius r. So it means that because we don't have any slipping, we have ma prime, where a prime, its acceleration, is our new frame of reference, equal force F, fictitious force F, plus force of friction F. From other hand, because there are no slipping, we have alpha equal a prime over r, which means that from second equation we have force of friction equal 2/5 ma prime. And putting these expressions to third equation, we have a prime equal negative 3/5a. Now we can go back to our original frame of reference and find that translational acceleration equal a prime plus a, which is 2/5a. That's answer D, and that was a solution for problem number 20. Problem number 21. Amora and Bronco are given a long, thin rectangle of sheet metal. It has been machined very precisely, so they can assume it is perfectly rectangular. Using calipers, Amora measures the width of the rectangle as 1 cm with a 1% uncertainty. Using a tape measure, Bronco independently measures its length as 100 centimeters with a 0.1% uncertainty. Which of the following are closest to the relative uncertainties they should report for the area and the perimeter of the rectangle respectively. Solution for problem number 21. Calculating the area involves multiplying the two measurements, and so the uncertainty in the area depends on the relative uncertainties of the inputs. Amore's 1% relative uncertainty dominates Bronco's 0.1%, so the result carries 1% uncertainty. It remains 1% because the area depends on each input to the first power. Calculating the perimeter involves adding the two measurements, and so the uncertainty in the perimeter depends on the absolute uncertainties of the inputs. Bronco's 0.1 centimeter absolute uncertainty dominates Amore's 0.01 centimeters, so the result carries his 0.1% uncertainty. Note that while the perimeter is approximately twice Bronco's measurement, the relative uncertainty is unaffected by this observation, so the answer is not 0.2%. So correct answer is B, and that was solution for problem number 21. Problem number 22. A cannon just above the surface of a spherical planet with mass m and radius r launches a particle with the speed v, where v greater than square root from gm over r and less than square root from 2gm over r. The initial velocity of the particle makes an angle theta with the vertical direction. Neglect drag. For what theta will the particle never collide with the planet? Solution for problem number 22. The launch speed is above the circular orbit speed and less than escape velocity. So in any case, orbit will be elliptical, and if angle is exactly 90 degrees, the launch point is the closest point of the elliptical orbit. So it means that in that case, the particle will never collide with the planet. But in other case, orbit of this particle will cross the surface of this planet. So that's not good. It means that only for angle 90 degrees we have good result. So it means that D is correct answer, and that was a solution for problem number 22. Problem number 23. A mass attached to a spring is performing simple harmonic motion with velocity v as a function of t and acceleration a as a function of t. Which of the following could be a graph of the curve a as a function of v over a complete oscillation? Solution for problem number 23. If displacement has a dependency from time as amplitude a multiplied by sine omega t, in that case velocity and acceleration have a dependency like this, and this is exactly parametric equation for ellipses. It means that the correct answer is C, and that was a solution for problem number 23. Problem number 24. A ramp with a height h is moving with a fixed uniform speed v to the right. A small block of mass m is placed at the top of the ramp and is released at rest with respect to the ramp. The block slides smoothly to the bottom of the ramp and onto the floor. How much kinetic energy does it gain in this process? Neglect friction. Solution for problem number 24. If a block reached the bottom of this ramp, it has a relative speed to the ramp square root from 2gh. It means that the absolute speed will be v final equal v plus square root from 2gh. And now we can count what is kinetic energy difference for this block. That will be delta k equal 1/2 mv final square minus 1/2 mv initial square, which is after calculations it's mgh plus mv multiplied by square root from 2gh. This is answer C, and that was a correct solution for problem number 24. Problem number 24. A ramp with the height h is moving with the fixed uniform speed v to the right. A small block of mass m is placed at the top of the ramp and is released at rest with respect to the ramp. The block slides smoothly to the bottom of the ramp and onto the floor. How much kinetic energy does it gain in this process? Neglect friction. Solution for problem number 24. First, we can find what is the final velocity of this block after it reaches the floor. That will be square root from 2gh compared to ramp, and v final equal v plus square root from 2gh compared to the floor. It means that the change of kinetic energy will be final kinetic energy, which is 1/2 mv final square, minus initial kinetic energy, which is 1/2 mv square. After calculations, we will get mgh plus mv multiplied by square root from 2gh, which is answer C, and that was solution for problem number 24. Problem number 25. Two masses are initially at rest, separated by a distance r, and attract each other gravitationally. If their masses are m and 2m, then they will collide after time t. How long would they take to collide if they both had masses 2m? Solution for problem number 25. Here we can use energy conservation and momentum conservation. First, let's use momentum conservation. We have mv1 equal to mv2. It means that v1 equal to v2, and the relative speed v1 prime equal v1 plus v2, or 3 times v2. From energy conservation we have this expression. Now we can use expressions for v1 and v1 prime and find that 1/3 v1 prime square equal change of energy. Here we have r prime, that's current distance between masses, and finally we have v1 prime equal this square root. Now let's see what happens if both masses have mass 2m. In that case, momentum conservation gives us v1 equal v2, relative speed equal 2v2, and energy conservation, this expression. Again, we can use expressions for v1 and v2 using v2 prime and find that v2 prime equal this expression. Now we can find a relation between v1 prime and v2 prime, relative velocities for two cases with the same distance, r prime. So we have v1 prime over v2 prime equal square root from 3/4 for the same distance, it means that time to take to collide back proportional to velocities. So it means that in second case we have time equal square root from 3 over 4 t, which is answer D, and that was solution for problem number 25.